is going to be our first of 2 lectures on this material. So today we are going to cover Thevenin and Norton equivalent circuits when there are only independent sources present. And then our class meeting on next Monday after our exam and all that kind of good stuff is going to be on Thevenin and Norton equivalent circuits with dependent sources. Okay, so I am intentionally not including dependent sources today. All right. So Thevenin's theorem states that any two-terminal linear electrical network may be replaced at the terminals by an equivalent voltage source VTH, so our Thevenin voltage, excuse me, in series with an equivalent resistance RTH, so a Thevenin resistance. So effectively what Thevenin's theorem states is we can replace any linear two-terminal network with a practical voltage source. Literally anything, as long as it's got 2 terminals, we can make it look like a practical voltage source in series with a resistor, okay? There are special rules for figuring out what that voltage VTH is going to be and what that resistance RTH is going to be. So that's what we're going to talk about now. Okay, so the Thevenin voltage VTH is the open circuit voltage across the terminals of the original network and the Thevenin resistance RTH is the equivalent resistance seen looking into the terminals of the dead network. Where the term dead network simply means that all of the independent voltage and current sources are turned off. So you're only looking at the resistances of the network, okay? So let's put this into practice by analyzing a circuit. So let's say that I have 12-volt source like so. Let's make this a 10 ohm resistor. Let's make this a current source actually. a 2 amp current source like so. A 6 ohm resistor. And then a 4 ohm resistor here. Okay. And our goal is to find the Thevenin equivalent circuit with respect to the 4 ohm resistor. We are going to assume positive polarity on top for finding our Thevenin voltage. So as it stands right now, we have a circuit, but we don't have a 2-terminal network, okay? So when we're finding the Thevenin equivalent with respect to a particular element in a circuit, which is what we're doing here, we are going to remove that element from the circuit. So that's what's going to give us our open circuited terminals that we're going to look at, okay? So in this case, because we're finding the Thevenin equivalent circuit with respect to the 4 ohm resistor, we are going to take the 4 ohm resistor out of the circuit and then do our analysis. So to find V Thevenin, we are simply going to analyze our original circuit with the 4 ohm resistor gone. So when we take that 4 ohm resistor out, we are left with a pair of open circuited terminals, okay? The Thevenin voltage is the voltage drop seen across these open circuited terminals. And we are told to assume that our positive polarity terminal of our Thevenin voltage is on top. So our goal now is to simply solve for this quantity VTH in any way that makes sense to us. So, do you guys have any thoughts on how we might solve for this voltage? I'm sorry, speak up. KVL. KVL is what I would use here. But in order to apply it, we need to make a couple of observations, but KVL is honestly what I would use here, okay? So let's make some observations. How much current is flowing through our 6 ohm resistor? What was that? 0. Why, John?
Because it has no way to get back to itself.
It's not part of a closed current carrying path, absolutely. So because the 6 ohm resistor isn't carrying any voltage, I can say from the jump that this voltage drop is 0 volts by inspection. Anybody have a problem with that? Right? Ohm's law tells us that if I is equal to 0, then V has to be equal to 0, because V is equal to 0 times R, right? So how much current is flowing through the 10 ohm resistor then? 2 amps, right? So I can see effectively by inspection that I have a voltage drop. Sorry, I'm putting this in the wrong way. Of 20 volts across my 10 ohm resistor, where the current is flowing into the positive polarity terminal. So that's why I'm just saying 2 amps times 10 ohms is equal to 20 volts, right? And so now, using Emmeline's suggestion, we can write the KVL equation. And in doing so, we would find that VTH, Sorry, this is supposed to be in black. Should be 20 volts plus 12 volts is 32 volts. Negative 12 minus 20 plus VTH is equal to 0, so VTH is equal to 12 plus 20. So there's our Thevenin voltage. Nothing particularly difficult about it. We can use any circuit analysis technique that we feel comfortable with to find this voltage. As long as we're finding the voltage drop across that open circuited set of terminals, we are doing it right, regardless of what circuit analysis tools we use to get there, okay? So we can choose our own adventure, whatever makes sense for the particular situation. So now we're going to find R Thevenin. So to find R Thevenin, we are going to redraw our original circuit. I'm going to make some modifications, so maybe don't draw it just yet. My 4 ohm resistor still needs to be gone because I'm looking in through those terminals. Right. But in order to find resistance, I need to be looking at a dead network, which means I turn my current source off. How do I turn a current source off? Open circuit. So I'm just going to erase the current source. And I also need to turn my voltage source off. How do I turn a voltage source off? Short circuit. So it seems pretty obvious to me that my Thevenin resistance here is simply 16 ohms. So putting these pieces of information together, we can say that our original circuit, I'm going to make a quick copy of it. You guys don't need to write this down again. I just want to illustrate something. These two circuits are electrically equivalent from the perspective of the 4 ohm resistor. So Thevenin equivalent circuits is used a lot in power analysis because we can find out the power flowing through the 4 ohm resistor using this Thevenin equivalent circuit much easier than we could figure out what the power is by looking at the original circuit. We've simplified it down into something that we could use voltage division to get the voltage across the 4 ohm resistor very easily, or simply Ohm's law to get the current flowing through it. And then from there, we could calculate the power, right? So the principal application of Thevenin equivalent circuits in actual electrical engineering practice is generally used for power analysis and for simplifying the analysis of more complex circuits, right? Because we can replace something big and gnarly with a practical voltage source, and we're going to wind up getting the exact same results, okay? So this was a simple example of finding the Thevenin equivalent circuit. It effectively does the exact same role as what we were doing with source combinations on Monday's class meeting, except that we can use it when we can't actually use a source combination, right? So when we were doing our maximum power transfer theorem stuff there at the end, we were using multiple source transformations to get our circuit down into a state like this where we had a practical voltage source or a practical current source connected to our load resistor. Now we have a different method to represent any two-terminal network or portion of a circuit that can be represented as a two-terminal network as a practical voltage source or practical current source using literally any analysis method that we feel like using. Okay, so to me, this is significantly more powerful than just simply relying on source transformations to go back and forth. Yes, sir.
So whenever you're in the resistance, would you treat current and voltage the same way you would in the pit?
So if we had a dependent source, and we're going to talk about this more on Monday, we can never turn a dependent source off. And so where that's going to be problematic for us is in determining the Thevenin resistance. Because since we can never turn the dependent source off, we don't have a simple resistor network anymore to analyze and use resistor combination techniques. So we're going to have to get a little bit creative by just using Ohm's law effectively. We'll talk about that more on Monday. All right. So this is Thevenin's equivalent circuit in Thevenin's theorem. So now let's talk about Norton equivalent circuits and Norton's theorem. So Norton's theorem states that any two-terminal linear electrical network can be replaced at its terminals by an equivalent current source I Norton in parallel with an equivalent resistance R Norton. Okay. So Norton's theorem says we can replace any two-terminal network with a practical current source, much like Thevenin's theorem says we can replace any two-terminal network with a practical voltage source. Okay. There are special rules for determining the current and the resistance that we use in a Norton equivalent circuit. All right. So the Norton current I Norton is the current measured between the short-circuited terminals. The current measured through, I guess, would be a better way to put it. The current measured through these short-circuited terminals of the original network and the Norton resistance R Norton is the equivalent resistance seen between the terminals of the dead network. So Thevenin resistance and Norton resistance are defined in literally the exact same way. They represent the exact same thing. So from this point on, you will never hear me refer to it as a Norton resistance again. I will always call it the Thevenin resistance. Okay, and that's what's typically done in practice. So let's take that exact same circuit and find the Norton equivalent circuit. So find the Norton equivalent circuit with respect to the 4 ohm resistor. Assume the down direction for I know. So one thing that I want to point out here, and we'll see this when we take a look at your homeworks, is that your homework problems don't really do a good job of saying which polarity to use for determining your Thevenin voltage, or sometimes they do actually, or your Norton current. I always try to make it a point to tell you specifically where the positive polarity terminal should be and what the direction of the current should be, so that it's very obvious what you're doing there, okay? It shouldn't matter in the long run, but I just want to be clear, if you are consistent, you'll get positive answers. Sometimes you'll get negative answers if you're playing fast and loose with things. Negative results for the resistance, which don't make a lot of sense, but it's because you did the wrong direction or did the wrong polarity with respect to each other. So anyway, so to find our Norton current, we are going to replace our 4 ohm resistor with a short circuit. And our Norton current, simply the current flowing through that short. So how are we going to solve for this current? And the short answer is however the hell we feel like. We can use any circuit analysis technique that we want. Emmeline. Right, the 6 ohm resistor would have been shorted out for this case. Yep. Absolutely correct. So how are we going to find the quantity I Norton? So we could use superposition here. Okay, I think I misunderstood your question. When we're finding the Thevenin voltage or the Norton current, we need to be looking at a live electrical network, meaning that all of our sources need to be on in order to determine those two quantities. We're only looking at a dead network when we're finding the equivalent resistance. Okay. Absolutely, we could use mesh. We could also use superposition. We could also use KVL, but we'll use mesh because that was your first suggestion. So I'm going to call this current I1 and this current I2. Because we have a current source, I should expect to have a current relationship equation. So we're going to say that 2 amps is equal to I2 minus I1. Now I'm going to write a KVL equation around the outside loop. since I have a super mesh there. So that's gonna look like negative 12 volts plus 10 ohms I1 plus 6 ohms I2 is equal to 0. Solving this. Throw this in a calculator real quick. I have a 2x2 system of equations. So my coefficient for I1 in my first equation is -1. My coefficient for I2 in my first equation is +1. My constant term is 2. In my second equation, my coefficient for I1 is 10. My coefficient for I2 is 6. My constant term is 12. Solving, I get I1 is 0. And I2 is 2, which I'm honestly a little surprised about. Let me double check that system. -1 I1, +1 I2. Yeah, you have to do a super mesh because there's a current source in the middle. Sorry, what? Yeah, yep. And then -12 plus 10 I1 plus 6 I2 equals 0. I don't see a mistake in my mesh. Anybody else get these results? Okay. I guess let me explain why I'm surprised about this, and maybe we'll take another stab at it. If we did superposition, so let me just write this down in blue here. So using superposition with the voltage source on and the current source off, I Norton prime would be 12 volts over 16 ohms is 0.75 amps. Seems reasonable. I Norton double prime, so this is going to be current source on, voltage source off, is going to look like 2 amps times 1/6 over 1/10 plus 1/6. So let me just see what this happens to be. My best guess is it's going to come out to be 1.25 to make the math work out both ways. It just seems interesting to me. That's exactly what it comes out to be. Okay, so 2 amps is right. I've got it the same answer both ways. So not what I was expecting, but it is what it is. So just to clarify here, I Norton is exactly I2, which we can see by an inspection. So I Norton is 2 amps, and that's what we got using the 2 different ways that we solved it. So from here, we could say that our original circuit is electrically equivalent to this circuit. Right, so that's how we were finding it. It wouldn't matter in the least if I turn this current source upside down, it would still be the exact same thing. So to be clear here, the 16 ohms of resistance came from when we determined the Thevenin resistance a little while ago, because the Thevenin resistance and the Norton resistance are the same thing. I thought it would be pointless to solve for it again. Okay. So what should hopefully be ridiculously obvious here is that the Norton equivalent circuit and the Thevenin equivalent circuit are indeed equivalent to each other. So they are effectively each other's source transformation as well. Right. So if we ever have a Thevenin equivalent circuit, we can get the Norton equivalent circuit by simply doing a source transformation and vice versa. So we can say pretty easily here that V Thevenin is simply equal to I Norton times R Thevenin, or we can say that I Norton is equal to V Thevenin over R Thevenin, or we can say that R Thevenin is simply the ratio of V Thevenin to I Norton, meaning technically speaking, we only need 2 of the 3 quantities to figure out what the third one is. So on your exams and things like that, because you guys are terrified of nodal analysis for whatever dumb reason, you could find the Norton equivalent circuit, Norton equivalent current using mesh analysis or something like that, find the equivalent resistance, and then use those 2 pieces of information to find the Thevenin equivalent voltage without ever having to do nodal analysis or anything like that to find V Thevenin for a particularly difficult circuit. Okay. All right, so let's take a quick look at your web work problems here. Trying to remember if there are any that are annoying to me. So if I'm not mistaken, this is homework set number 9. You're asked to find the Norton equivalent circuit, and you're told the current is flowing from A to B and flowing from B to C. I think I rewrote that because it was very unclear earlier. This one isn't particularly difficult. Find the Thevenin equivalent and then use simple power relationship. That's not particularly bad. Nothing really wild or crazy here. Okay, so let's take a crack at this one here. So this is doing the exact same thing, but from a slightly different perspective, okay? So in this problem, you're given terminals to find the Thevenin equivalent with respect to, not a particular circuit element. All that really means is that you don't need to take anything out of the circuit. So I'm going to redraw this circuit here. R1 is 100 or 11.5 ohms. So let's throw this on a new page. And then we have a current source, and the current is -4 amps. So I'm just going to draw that as +4 amps down because I don't like negative numbers. R2 is 19.5. R3 is 5. R4 is 17. Then we have a voltage source, and it is 44 volts. And we are asked to find the equivalent between terminals A and B for the first part, right? Yes, A and B and then C and D. So let's worry about B. Okay. So how I would approach this problem is to redraw it very slightly differently. Okay. And that very slight difference is to extend this node all the way out to here and call this terminal A, and extend this node all the way out to here and call this terminal B. And then go about my day, right? So I'm mentioning this because I have seen students numerous times take the 11.5 ohm resistor out of this circuit and then find the Thevenin equivalent with respect to that, which is not what you're being asked to do here. You're being asked to find the Thevenin equivalent circuit with respect to this set of terminals. The terminals are already open circuited, as we can see by extending them to the left. So this is where we find the quantity VTH. This is what we'll short out to find our Norton current. This is what we'll look into to find our Thevenin resistance, okay? So let's find the quantity VTH first, all right? So anybody have any thoughts? No, we are doing it with respect to the terminals A and B. So we're looking for the Thevenin equivalent seen between terminals A and B. And just to be clear, find the Thevenin equivalent of the network between the terminal pairs. So if we're not finding it with respect to a particular element, there's nothing to take out of the circuit. We already have an open circuited set of terminals that we are looking at. That is the distinction I am trying to make here. Okay. When you find the Thevenin equivalent or the Norton equivalent with respect to a particular element, that element needs to be removed. If you're finding it with respect to an open circuited set of terminals, you don't need to remove anything. Just use those terminals. That's where your open circuited voltage is going to be measured. You're going to short circuit those terminals to find your Norton current. Okay. Yeah, no, it's a very good question. I'm trying to make sure everybody is on the same page. Yes, sir.
Electrical equivalent to the current source and
Right, but if I did that, just to be clear here, I'm going to draw where it would be in blue. It will be between those two nodes, which I'm not sure that that actually helps me any. So on the right-hand side here, we could replace this with a current source, absolutely, which I don't necessarily have a problem with, but let's just kind of stop and think about things for a second before we just start throwing crap at it to see what's going to come out. There's no wrong way to do this, okay? So I want to be clear about that. Either of those two suggestions or even both of them could be used. The question does it make it any easier? Or is it just making the circuit look different for the sake of it looking different? And to me, it seems like we're just making it look different for the sake of making it look different. Nick, did you have a question, comment, suggestion? Nodal seems perfectly reasonable. Nodal analysis, because we're trying to find a voltage, okay? Don't have to change the circuit at all. So I'm going to identify my nodes here. Oops, not what I meant to do, but it'll be okay. So here's one node. Here's another node. Here's another node. Here's another node. Like so. Nick, since you made the suggestion, I'll give you first crack at defining where ground should be. The bottom, I agree. Generally speaking, if I'm trying to find the Thevenin voltage with nodal analysis, I choose my ground terminal to be the negative polarity terminal of my Thevenin voltage. That's not always going to be the case. If I have a whole bunch of voltage sources, I'm going to put it wherever the most voltage sources are connected and stuff like that. But generally speaking, that seems like a perfectly reasonable place. This nodal voltage VA is now the exact same thing as the Thevenin voltage. I'm going to call this VX, this guy VY. The reason why I'm not doing B is because the letter B is associated with my ground terminal, and I don't want it to be confusing. So I have a voltage source, so I have a voltage relationship equation. Vy is equal to 44 volts, because this supernode here, every time I have a voltage source, I have a supernode. Because it contains ground, I'm not going to write a KCL equation at node Y. So I'm going to have a KCL equation at A and a KCL equation at X. And that's what I'm going to use to solve for this thing. So KCL at A is going to look like VA over 11.5 plus 4 amps plus VA minus VX over 19.5 is equal to 0. Bless you. KCL at X is going to look like VX minus VA over 19.5 plus VX over 5 plus VX minus VY over 17. That looks too much like a 12 to me. Is equal to 0. And now I'm just going to solve this system of 3 equations. So in my first equation, my coefficient for VA is 0, my coefficient for VX is 0, my coefficient for VY is 1, my constant term is 44, which I put too many 4s there. In the second equation, my coefficient for VA is 1 over 11.5 plus 1 over 19.5. The calculator is giving me a syntax error here, so let me think about a way to fix it. 1 over 11.5 is the same thing as 2 over 23, right? And 1 over 19.5 is going to be the same thing as 1 over 39, or excuse me, 2 over 39. I think my calculator didn't like decimals in my fractions, so I'm just trying to clear that out. My coefficient for VX is negative 1 over 19.5, so negative 2 over 39. My coefficient for VY is 0. My constant term is negative 4. In my third equation, my coefficient for VA is negative 2 over 39. My coefficient for VX is positive 2 over 39 plus 1 over 5 plus 1 over 17. My coefficient for VY is negative 1 over 17. Constant term is 0. Solving, I get VA, which is the same as VTH, is negative 27.528. VX, for what it's worth, is 3.794. And VY comes out to be 44 volts. Obviously. Anybody get these same results? Good deal. All right. So we figured out our Thevenin voltage. So let's take a crack at our Norton current. Okay. So redrawing my circuit. I'm gonna have up here, short circuit. Four amps. 19.5. 5. 17. 44. I want my screen got smaller, so make it big like it's supposed to be. So when I'm finding my Norton current, I'm going to short circuit those terminals. And I'm going to find my Norton current direction down. So what are we going to use to solve this? That's one option. Not saying it's wrong. I'm saying there's a way easier way. Well, no, mesh will be okay. We could, but let's get in the practice of solving for all of the different things so we make sense here. Let's do mesh. Why not? So how many meshes do I have? While you're technically right, I'm going to use 3. Because the short circuit is shorting out the 11.5 ohm resistor. So instead of bothering to write 2 equations where I know one of them is just going to be 0, I'm just going to call this thing, let me use a different color. One mesh. Right? I know that no current is flowing through the 11.5 ohm resistor because it's in parallel with a short circuit. So I'm just going to not waste any time proving that using a system of equations, which is also going to let me have a smaller system of equations. And here we would have I2. And over here, we can have I3. So because we have a current source, I need a current relationship equation. So that's going to look like 4 amps is equal to I1 minus I2. Just as a quick observation over here, we can notice that I Norton is simply negative I1. Now I'm going to need a KVL equation around my super mesh. So this KVL equation is going to look like, so this is KVL at super mesh 1, 2. We're going to have 19.5 ohms times I2 plus 5 ohms times I2 minus I3 is equal to 0. Because there's literally no resistors in the path that current I1 is taking, it doesn't show up here. Okay. Then we're going to have KVL at mesh 3, which is going to be 5 ohms times I3 minus I2 plus 17 ohms I3 plus 44 volts is equal to 0. solving the system for I1, I2, and I3. So in my first equation, my coefficient for I1 is +1, my coefficient for I2 is -1, my coefficient for I3 is 0, constant term is 4. In my second equation, my coefficient for I1 is 0, my coefficient for I2 is 19.5 plus 5. My coefficient for I3 is -5, my constant term is 0. In my third equation, my coefficient for I1 is 0, my coefficient for I2 is -5. Coefficient for I3 is 5 plus 17. My my constant term is -44. Solving, I get 3.572. -0.428. And -2.097. Which means I Norton is -3.572 amps. Should make a lot of sense that I Norton needs to be negative here because V Thevenin was negative and the ratio of those things should be a positive resistance. So did anybody else get these results? Okay. All right, so just to check our work here. Our Thevenin resistance should be, scroll up and find it, -27.528 volts. Over -3.572 amps. Comes out to be 7.707 ohms. There is some rounding error there, so as long as we're in the ballpark of 7.7 ohms, we've done this right. So now let's find our equivalent resistance. So we have our open circuited terminals. 11.5 ohms here. Our current source is open circuited. I believe this is 19.5 ohms, 5 ohms, and 17 ohms. If I have the wrong resistor value anywhere, please let me know, but I think I remembered it all correctly. So this looks like 11.5 ohms in parallel with 19.5 ohms in series with the parallel combination of 5 and 17. So 19.5 plus 5 times 17. Over 5 plus 17, I'm going to store that as X, and then 11.5 times X over 11.5 plus X, 7.707 ohms. So it appears we've done everything correctly. All right, so just to recap things here. When you are finding the Thevenin equivalent circuit or the Norton equivalent circuit with respect to a particular circuit element, you remove that element from the network and do your analysis. Removing that network leaves behind a set of terminals that you are using to measure the Thevenin voltage across, look into to find the Thevenin resistance, and allows you to short circuit in order to measure the Norton current. if you are finding the Thevenin equivalent circuit or Norton equivalent circuit with respect to a set of terminals, don't take any elements out of the circuit. Just use those terminals that you're provided to do all of your analysis. So I believe in the in-class assignment, I give you one problem finding it with respect to a particular element and another problem finding it with respect to a set of terminals. So have at it. If you have any questions, Emmeline. Yeah, so we could have, if we found the Thevenin resistance and we found the Norton current, we didn't really need to find VTH at all because we would get the exact same result as just multiplying RTH times I Norton. I found all three things so that we could check our work here. It is always the equivalent resistance looking into the terminals that we're asked about while looking at the dead network. That is the literal definition of Thevenin resistance. It is the equivalent resistance looking into the terminals of a dead network. So notice here that my current source isn't there. My voltage, because it's an open circuit, my voltage source has been replaced by a short circuit. That's what a dead network means. Turning off all of our independent sources. Yes.
This could theoretically be used for our assessment.
Absolutely.
So what? An example of a question that.
The power factor, not the power factor stuff, the finding the equivalent. So finding the resistance that allows you to have maximum power transfer and all that kind of stuff. It's the Thevenin resistance. Yeah, so everything, including what was done on Monday, is on your exam. That being said, you can use this on your exam, nothing's wrong with it. But it's not, you're not specifically being tested on. This is the first topic that you will be tested on.
Right, you would another idea. It wasn't source transformation, why did you?
So my other idea when looking at this was actually to do superposition because I can see really easily that the contribution from the 4 amp source is -4 amps. So that I only need to look at it with the voltage source on to actually do any analysis whatsoever. And with the voltage source on, I could find the voltage drop across the 5 ohm resistor, and then that voltage drop divided by 19.5 ohms gives me the Norton current. So just voltage division and then an ohms law.
So that would just open up that 4 amp instead.
Right. So if I open circuit the 4 amp source and recognize that the 11.5 ohm resistor isn't in there, what it looks like is 44 volts in series with 17 ohms, and then I have 5 ohms in parallel with 19.5 ohms. Right, which is a very easy problem. Yeah. So to me, that's easier than mesh because it's voltage division and ohms law -4.